So I'll give a bit of a tour d'horizon of blind signatures and what they have, like some schemes, what they have been originally proposed for, and what they are used now in the blockchain context. Good, so who has never heard the word digital signature? Good, so you know what it is. What's a blind signature? So whereas here the signer has a key pair, can use his secret key to sign a message, create a signature sigma, and this can be verified using his verification key. In a blind signature scheme, we have a second party, Yuma, the user, and now she has the message and she runs a protocol at the end of which she obtains a signature under Sai's verification key in a way that Sai doesn't know what message he signed. So this is called blindness, and we moreover want that if the signer later sees the signature, he doesn't know which signing session it came out of. On the other hand, we want some guarantees for the signer, which is captured as one more unforgeability, meaning that if the signer runs this signing protocol n times, then he's guaranteed that there won't be more than n signatures. And that's called one more unforgeability. You can't have more signatures than you asked for during these signing protocols. Okay, what they were originally introduced for is electronic cash, e-cash, predating Bitcoin by quite a bit, and I'll talk about this in a bit. They were also used for e-voting, anonymous credentials, and then more recently they've there was a lot of renewed attention. They were used in contract tracing and a lot of privacy-preserving authentication, like advanced VPNs, private relays, private access tokens, privacy pass, and Bitcoin blind coin swaps, which I'll also talk about. So to start, who has never heard of RSA signatures? Good, here's a quick refresher. So the RSA function is defined by a public modulus n, that's a product of two secret primes. Then we have e, an exponent, think of it as being 3. And then the RSA function takes a number and maps it to, so it maps x to the power of e modulo n. And that's something that you can efficiently compute, but it's hard to invert. So we believe that if I give you a random image output of this function, you cannot find the pre-image. So it's a one-way function. And what makes it particularly interesting is that if you know some secret information, then you can actually invert it, and that's often called a trapdoor one-way function. And this secret key, you can compute it from the secret primes P and Q. Okay, I'll show you like a high-level description of the RSA signature, because then I can easily explain how to turn this into a blind signature. So the RSA signing, so sign a message, if you have set up this function as the signer, you first hash the message to make it a number between 0 and this modulus n. And then the signature is simply you apply the inverse function, which only you can do because you have the secret key. That's defined as the signature. And since from the signature you can apply f, everyone can, you can easily check if the signature is valid by checking if f maps it back to the hash of the message. Okay, so now David Chaum had this idea that you can actually define a blind signing protocol for this. So we have Sai the signer, Yuma the user. And what the user does is she takes the hash of the message and then she blinds it by f applied to r, where r is some random value, right? So that's like completely hides the message to the signer. So if the signer now applies the inverse function to m prime, then you can see that the f's cancel out, and so the user can obtain an actual signature by just dividing out r, right? Simple algebra. Okay, what has this first been suggested for? As I said, it was eCash in, which is now called as Chaumian eCash, in a classical setting when there were still central banks. So the idea was that a client has an account at the bank and then she can withdraw an electronic coin. And to get anonymity so that the bank doesn't know which coin which client withdrew, we use blind signatures. So the client would pick a random serial number, high enough entropy so that it's unique. And then we'll get a blind signature on the serial number, and that will constitute her coin. Just some serial number that's signed by the bank. And she can now spend this coin with a merchant, for example, Marcellus. However, what's the problem with electronic cash in general? Double spending. What if she also spends her coin with someone else? Well, in this very simple scheme, that's easily fixed because the merchant, before actually giving out the goods, he would just ask the bank if this coin had not been spent yet, right? So the bank doesn't know which coins are around because they were blindly issued, but the bank knows which coins have been already deposited. Okay, so if it's not spent yet, the merchant will give the goods. Okay, so that's all very anonymous and 1980s. So you might wonder, what can blind signatures do for us in the blockchain era? So let's look at one example. Who has heard of the Lightning Network? Good. So the Lightning Network, no? Really? Okay. Lightning Network is a way that lets people transact with Bitcoin off-chain. So you use the security of Bitcoin, but you don't need to put every payment on-chain. And this can be done by opening so-called channels. And since to open a channel, you actually have to put some Bitcoin in there, you don't want to open a channel with every potential receiver. So what people do, they use payment hubs. So Alice has a channel to the hub, and if the hub has a channel to Bob, then she can send money to Bob via this channel. And so the idea, okay, so what is, how do you open a channel? Well, you put a Bitcoin transaction where you'd need two signatures to for this transaction to be valid. So one signature by Alice and one signature by the payment hub. And so the idea of the Lightning protocol is that if Alice pays the hub, but she often pays the hub, they don't want to put every payment on chain. So what she does is she makes such a transaction for some value and then gives it to the hub. The hub doesn't put it on the blockchain yet. And now if Alice wants to pay again, she can just replace this transaction with a higher value, right? So you can constantly send more money by just updating these transactions. Same thing for the hub and Bob. And once the hub actually wants to take the money, it takes the last transaction with the highest value, signs it, and sends it to the blockchain. And that would be a closing of the channel. Okay, so here's a problem, which is that you need to trust the hub, right? So if Alice wants to send money to Bob and she signs this transaction here, the hub could just close this channel, take the money and not send anything to Bob, right? That would be a problem if you had to trust this hub. So there's this very nice idea which solves the problem of that. So actually what you want is you want these two transactions to be atomic, meaning that either both of them go through or none does, right? This way the hub can't steal the money because either the hub receives the money and Bob as well, or the money just stays where it was. And so to realize this seems hard because you can't just encode arbitrary conditions in Bitcoin because of its reduced set of instructions. But there's one instruction that it supports, which is, I think, just an artifact of how Bitcoin addresses work. But what you can do is you can encode the following statement into the transaction. So the hub chooses some random value x, hashes it, and then encodes y in this transaction so that you can only, so this transaction only becomes valid if you put this secret value x in there, right? So now for this transaction to go through, you need the signature by the hub, Bob's signature, and also this pre-image of y that's encoded in the transaction. That's called a hash lock. And so what the hub can now do is, if it created this hash lock, it can sign this transaction, and it knows that as long as it doesn't reveal this x, no one can take this money, right? So what happens next? Alice now puts the same condition in her transaction, right? So to take this transaction here, the hub would actually have to reveal this value x, which once it does it, allows Bob to take the second transaction, right? So this way we link the two transactions. If the hub takes the first one, Bob can take the second one. If the hub doesn't, no one can take the second one, and so the hub is also protected. Is that clear, this sequence of events? Questions? Are you amazed by the Lightning Network?
How can Alice do this because she doesn't know X?
So that's kind of part of the protocol, that the hub tells Alice, sorry, she doesn't know X. The hub tells Alice Y. Pardon? Y is enough to make this transaction. Now to take this transaction, so Alice signs it, she wants the Bitcoin to go through. The hub, if it wants to take the Bitcoin from Alice, has to publish, well, accompany the transaction with this value X. It's sent to the blockchain. Everyone sees it. Hence Bob sees it, and hence Bob can take the money. Okay.
Just to make it easier,
yes.
maybe to make it easier, it's like simple as a reverse workflow, because the secret comes from the end
Yes.
receiver, and this secret with high entropy and all of that should go back to the first sender.
Exactly. So if
it has to go through all of them, you get like it doesn't matter how many hubs,
yeah.
because these hubs has to do to send these hashes
Yeah.
backward to be able to receive the money.
Exactly. So you could have many hops, and then the secret would go from the last hop to the first one, and this way either everything goes through or nothing does. Okay, so in terms of financial security, that's good, right? No one can steal each other's Bitcoins. But what about privacy? So if you have not only this Alice transacting with this Bob, but there's another Alice transacting with another Bob, and still a third Alice and a third Bob, then you actually see by looking at these Bitcoin transactions who sent money to whom, because the hash lock, this value is the same in the ones that belong together, right? So this is completely linkable. So a question was, can you have the same functionality, the same security, but in a transparent way so that you don't see who sends money to whom? And that's what Tumblebit, which was a proposal like 10 years ago, achieved by Heilmann et al. And the idea was to use blind signatures for this in a very specific way, namely to replace this condition of asking for a hash preimage to redeem a transaction by the condition that you need a certain signature under the hub's verification key to take this money, right? So we have the same guarantee, right? Before it was only the hub that knew the preimage. Now it's only the hub that can create this signature because it's a signature by the hub. But what's different now is that how can Alice get this signature? Before, she had to put the same condition in both transactions, and that's why they were linkable. But now we can use the fact that you can blindly do RSA signatures. So what she can do is she can encode the condition that if ever the hub gives her a blinded signature, it can take the money. So that's kind of the overall idea, because if the hub now takes the money, the hub gives her a blinded signature, she can unblind the signature, give it to Bob, and now Bob can take the money. Right? So this way, because you can blind and unblind signatures, you can break the link between these two transactions, but still have the same functionality that Bob can take the money if and only if the hub takes the money. What's the problem with this? Yes?
Is it important, like, who samples the message?
It's well, in this, what they do is actually not really an RSA signature, but just they don't hash the message. So if Bob sampled the message as an image of something it knows, he would also know the pre-image. That's why it's in their protocol. It's important that the hub samples it. Okay, what's the problem? That RSA signature verification is not an opcode that Bitcoin supports, right? You can't make a Bitcoin transaction and say only if you give me a RSA signature on a certain message that verifies under some key, this transaction will go through. So they kind of have to work around it. And what they do is they put the standard Bitcoin transaction here, and then they let the hub send the encryption of the hub's transaction signature, so whatever Bob would need to take this money, the hub encrypts it under a key. That's the signature that it's actually asking for, right? So now we have the same functionality. If Bob has the signature, then he can decrypt the ciphertext, get the signature on the transaction, and thus this transaction is signed and Bob gets the money. There's also, on the other side, we have to work around the fact that you can't just encode RSA signatures in Bitcoin. But for that, there were already protocols such as ZK contingent payments, which is a way that using zero-knowledge proofs that lets you buy any information that you can efficiently verify. So any witness of an NP statement for Bitcoin in a fair way. So either you get the Bitcoin and the sender gets the information or no one gets anything. So that was first proposed by Maxwell, and then there were some problems, and then there were still some problems, and hopefully my version is then the one that works. What Tumblebit does is they avoid ZK snarks because it's a very specific statement that needs to be proved, and they use cut and choose proofs, and they can do a bit more efficiently. Okay, but what about this side of the protocol? How can Bob be sure that C is correct, right? He has to rely on the fact that if ever he gets this signature sigma, he should get a signature tau on this transaction, right? He needs to be sure that that's really the ciphertext that the hub claims. And so for this, again, either you throw a snark at it, or in Tumblebit, they do cut and choose proof. Okay, let's take a step back and look at what functionality we actually want to achieve here, which is that we want some way so that Bob gets a Bitcoin if and only if he knows some signature. And if you think about it, if this was not an RSA signature but a Schnorr signature, which is supported by Bitcoin, and if the signature was just the signature on a transaction, and that's like by definition this protocol, right? If Bob has this signature by the hub, he has the Bitcoin because the transaction is signed. If not, he doesn't, right? So if we can do the same thing with Schnorr signatures, everything simplifies because that part of the protocol basically works out of the box. So what we would need is a protocol for between Alice and the hub that allows her to blindly buy a Schnorr signature for Bitcoin, right? Then we have both sides of the protocol. You have as much time as you want. Yes, I'm being very fast, so I'll take a break now. Okay, so if we want to blindly buy a Schnorr signature, we should look at Schnorr signatures, and we should look at blind signing for Schnorr signatures. Okay, so I hope most of you are familiar with Schnorr signatures. Here's a quick reminder. So they are defined over nowadays an elliptic curve group of order Q generated by some generator G, and a hash function that maps strings to ZQ. And a key pair, a secret key is a uniform element of ZQ, and the verification key is just X times the generator. This is additive notation. I guess you're more used to G to the power of X, but for elliptic curves, it's in general nicer to write it this way. How do you make a signature? You first create this ephemeral key pair. So the signer picks some random little r, computes capital R equals little r times G, and this will be the first element of the signature. It then hashes this group element together with its public key and the message, and that gives a value C that's often referred to as a challenge. And the second element of the signature will then be R from this first step here, plus the challenge times the secret key modulo Q, and that's the signature. you can verify that this S was computed this way by basically evaluating in the exponent, or like imagining that you multiply the generator to this equation. Then you get that S times G should be R times G plus C times capital X, which is exactly how you verify a signature. Okay, that's Schnorr. Now the question is, can you also do like a nice blind signing protocol with Schnorr? And the first thing you might think of is, well, if only the user knows the message M, then why don't we let the user compute this challenge here, right? Because the signer won't know M. So first approach would be the signer sends the first signature element that doesn't depend on the message to the user. The user creates this hash value, sends it to the signer, and then the signer makes the second signature element. Would this be a blind signature? No, because I said blindness means that if I later see a signature as a signer, I don't know which signing session this comes from. And here the elements R and S were just sent by the signer, right? So it's obviously not blind. So Schnorr himself came up with this amazing way of blinding things so that you can actually make it in such a way that the user obtains a signature that the signer doesn't know. And so the way it works is that the user chooses two blinding values alpha and beta, gets this first value R, but then blinds this R to some other value R prime using these blinding factors, which will be the first element of the final signature. So the user hashes this R prime to compute the challenge. Can't send the challenge to the signer because that would break blindness again. So it again blinds this C value by beta, sends that over to the signer, and then the signer just does what it did in the original scheme. So it uses the original value R and this double blinded value C prime, sends it back to the user, and then magically the user using the value alpha can take this value S, produce S prime. That's exactly the second signature element that you need. If you plug in everything, you see that it works out. So blindness is not too hard to see because you can actually show that the signer doesn't get any information because it just sees random elements. The more interesting property is one-more unforgeability, right? Because the signer kind of does things to elements he doesn't have any control about, so it's not clear whether this is unforgeable, and I'll come back to this. Good, but let's quickly see how since now we have this blind signing protocol, how you can buy a signature blindly for Bitcoin. So recall this was our, this is where we ended the discussion before. We know how, like, if this sigma was a transaction signature, this part of the protocol, we have it. But now how can Alice get a blind signature on some message if and only if the hub gets her Bitcoin in exchange? And this goes back to an idea by Jonas Nick from Blockstream for blind coin swaps, where, so the idea is that we want a protocol so that Alice gets a blind signature RS, the hub gets the Bitcoin in an atomic way, right? Either both of them get what they wanted or no one gets anything. So the idea is that they start this blind signing protocol. So the signer sends over the value R, the buyer sends the blinded challenge, and then the signer doesn't reply, right? Because otherwise the buyer would have the blind signature, but the signer didn't get any Bitcoin yet. But they use a protocol to buy a discrete log, which uses adapter signatures. And unfortunately, for time reasons, I won't go into that, but it's very simple and very cheap to do. Okay, so that now shows us that if you, since we have this blind signing protocol for Schnorr signatures, we can do these anonymous payment channels in a much more efficient way. Questions?
Just out of curiosity, so in these adapter signatures, right, like in many of the applications, like there is a third party, right, that releases the evil. So, but you're not using it in this way.
No. So the idea is that both of them, they set up a multi-sig transaction, which forces which kind of fixes the first element of the multi-sig, so this R. And now the seller of the discrete log basically returns this S value, but shifted by the log it wants to sell, and only then the other party will sign its part. And so when the seller wants to take the money, it has to produce the actual unshifted Schnorr signature, and since from the two you can now extract the discrete log. Yeah. Okay. Good. So what was that? Nothing. Okay. Last thing to talk about is this one more unforgeability of Schnorr, of this blind Schnorr issuing protocol. So what do we know? First, what do we actually mean by it, right? And I argue that what you need is a security notion under a concurrent attack. And what do we mean by that? Consider the situation: you have the signer and the user, and there might not be just one user, Yuma, that wants messages signed blindly, but there might be many users. There might be Hussein and Yuri, and say Yuri starts, opens a signing session, and then disappears into space. Then the signer cannot just wait until Yuri replies before ever opening a new session, because otherwise he would be susceptible to a denial of service attack very easily, right? So we need the signer to be able to open many sessions in parallel, and that means that we want the security notion needs to kind of reflect this. And so in the game where an adversary wants to forge a signature, we also need to allow the adversary to open many signing sessions in parallel. And that's a notion that Schnorr considered for his blind signing scheme. And he gave a proof and showed that in an idealized model, which is the generic group model plus the random oracle model, and using an assumption, you can prove his scheme secure. And yeah, we relaxed this and replaced the generic group model by the algebraic group model to make it a bit less idealized. But Schnorr actually showed more, namely that if you can break this Ross problem, then that actually leads to a concurrent attack on the system, right? So they are kind of equivalent. Now, there were always some doubts as to how hard Ross really is, but unfortunately, a few years ago, Ross was completely broken by Ben Hamouda et al. And so that meant that if you can, so what they showed is if you have this, someone uses this blind signing protocol and you can open enough parallel sessions, then you can actually obtain more signatures than you open sessions. And so if you think of the eCash scenario, you would have more eCoins than the bank thinks that you withdrew. So the open question that we addressed was, can we define a blind signing protocol for Schnorr signatures, right? So often these blind signatures, they just invent the scheme and then you have some new signature format. But for our applications like Bitcoin, we needed a blind signing protocol that really produces the Schnorr signatures as specified by Bitcoin. And that was not known how to do that. So that's what we did in a work with my student Matthias Wolf at Eurocrypt last year. And the idea is, in hindsight, not that complicated. So if you look at how the attack works, is that so the adversary wants to attack the signer. It opens a lot of signing sessions, so it gets a lot of R values. And from these, it now computes the C values in a malicious way, and that's what enables the attack. So if you want to prevent the attack, then you could try to force the user to compute C correctly. The problem is that, what does correctly mean? C is just some blinded random value. So what we did is we first let the user commit to all her secrets. So once these values alpha, beta, and m are fixed, there's only one value C that's correctly computed according to the protocol specification. And so now she can add a zero-knowledge proof that proves that the C that she sends is correctly computed. So that prevents the attack, but actually you can even prove that this protocol satisfies this one more unforgeability under concurrent attack, assuming that Schnorr itself is unforgeable, which seems like an obvious thing you assume if you use the scheme, and soundness of this proof system. Yeah?
But for the proof, isn't it enough just to prove some linear relation of the discrete logs? Or
That's the annoying thing. So that's, yeah, that's, I mean, yeah, I haven't planned to talk about this a lot, but it really depends how complex this proof protocol is, really depends on what hash function you use and what elliptic curve. You can use like pairing-friendly or snark-friendly elliptic curves, like the baby chop curve. You can use Poseidon, and then it becomes very efficient. But it's cheating because we want the Bitcoin Schnorr, right? So you need to use sec_p as the elliptic curve and SHA-2 as a hash function, and that's very unfriendly to snarks. And so we gave some implementations using Groth16, Plonk, and Spartan, where we hope that Spartan would be more efficient because it doesn't use pairings, but at least the libraries that we used weren't too promising. But talking to snark implementers, they think that this can be proved in a few seconds. So for us, it took like a minute to generate the proofs. Okay. Last thing, when looking at this protocol, we realized that, okay, the user needs to prove some statement involving the message that she wants a signature on. So what she could actually do is she could prove any predicate of the message as well. And that kind of led to a cryptographic primitive that surprisingly had not been considered before, which we call predicate blind signatures, which kind of makes this concept of blind signatures arguably more reasonable, because in classical blind signatures, the signer has no idea what he's signing. So what we proposed is that they agree on some predicate of the message, some property that the message should satisfy. And so our predicate blind signatures now guarantee that the signer only signs messages that satisfy the predicate. And the user still gets the best blindness guarantee, which is that, the signer doesn't learn anything more than that the message satisfies the predicate. Okay, now this is a generalization of partially blind signatures. One speculative application of this concept, so meet Sam, the signer, who runs a cryptocurrency exchange, and Alice has an account with the signer, so she doesn't have manage her own keys, but let's trust Sam to do that. So the question is, can Alice or Yuma or any client make an anonymous payment, right? If she wants to buy something and she needs Sam to sign this transaction, Sam knows what she bought, right? So here's an idea. Can't the user just create the Bitcoin transaction from one of Sam's addresses and then just ask him to sign it blindly? Well, I guess if this was just a standard blind signature scheme, Sam wouldn't do that, because otherwise she could make him sign anything and maybe all his money is gone afterwards. But using these predicate blind signatures, there's actually a reasonable protocol, which is that they agree that whatever he's signing is a Bitcoin transaction with an upper bound on the amount. So the predicate says that this transaction that I'm blindly signing does not spend more than V value of Bitcoin. And so then the exchange can just debit the user's account by this value V, and we get some privacy, of course, depending on how many people use this and what amount they ask for. Good. With that, let's finish and have coffee or different kind of beverages. Thanks.